Rivo, and I work in Veriff as fraud engineering lead. With this talk, I'm hoping to give you a glimpse into how we catch fraud and how we use data and obviously Python to do that. Let's start by looking at what Veriff does. Veriff's core business is online identity verification. For example, we enable you to sign up for a bank account without having to physically go into a bank. But our story began years ago with some blue string. This is Karel, our founder and CEO. Many years ago, Karel was growing up on a farm and he needed some biodegradable string for hay bales. He found exactly what he needed online, but unfortunately couldn't buy it because PayPal required customers to be at least 18 years old. So, one sunny afternoon, Karel did some document tampering fraud, changed his year of birth, and voila, he got the blue string. Years after that, while working for Wise, he saw that the same issues are still present, and that's how Veriff got founded. And today, my team is essentially trying to stop others from doing what Karel did. Let's look at how identity verification works from user's perspective. It's really very easy. You first take a photo of your document, then a photo of yourself, and then you just wait a couple of seconds until we give you a decision. And the decision is usually either approve in case everything was fine, or decline if we see that something is missing or wrong. And we make most of those decisions automatically, but we also have human verification specialists who act as a backup in case of more complex cases where automation is unable to do confident decisions. And if that wasn't difficult enough, we also deal with fraudsters. Fraud prevention is a pretty important part of Veriff's offering, so we have multiple teams tackling it. My team in Veriff mostly deals with technical and pattern fraud, meaning multiple verifications where the person is the same or using the same document, the same device, or something similar. Think somebody trying to create lots of fake accounts. We try to stop those people. We also have a team for document fraud. They try to detect whether the document is real or tampered, and they also check if you're showing a physical document instead of just a screenshot. Importantly, we also have a fraud operations team. They are the ones who monitor the verifications on a daily basis, and they usually are the first ones to encounter new cases of fraud and then try to figure out ways to stop them. And we also work closely with verification specialists who are our ultimate line of defense. To show how it all comes together, let me tell you a story. This happened about a year ago when we started noticing verifications from this group of Vietnamese fraudsters. They were creating lots of fake accounts, and while some of them got caught by our verification specialists or quality assurance, they seemed to be able to somehow avoid our automated detection by using a variety of devices, VPNs, and literally a pile of fake documents. We see some really interesting stuff every now and then. Unfortunately, I can't share most of it because we protect people's privacy, even if we're pretty sure that they are fraudsters, like 99.999% sure. Before continuing, let's look at how we generally find fraud. First, we check for common data points that link the verification with some of the previous ones. For example, we might see that the device is the same or document number is the same as in one of the recent verifications. Secondly, most fraud is actually something that we have already seen before, so we have various rules in place to find suspicious verifications. As an example, we've seen lots of fraud involving UK driver's licenses, so we have some special checks for those. And finally, there's also some stuff that I really can't go into because the opposing team could also be watching. But in general, it's all based on data. We start with some raw data that we collect from the user, either in form of the images or some device information, and then we iteratively process it until finally ending up with decision. And once the decision is made, we also want to do some analytics afterwards to see what happened and which kinds of decisions we made, for example. Now, coming back to our case of fraud, I said that we catch most of them because they are trying something that we have already seen before and we can easily detect that. But this group was one of the smart ones. They were trying something new and they were also able to change their approach quite quickly. See, back in the day, engineers needed to be involved in making any changes to the fraud detection logic. Our rule sets were mostly implemented in this huge SQL query, and rolling out changes to that was pretty cumbersome and slow process, and that really hindered our ability to react quickly. So even if we had a solid idea on how to stop a particular attack, our reaction time was pretty problematic. And due to our growth, we had started to see more and more cases where complex fraud like that would go on for too long. But luckily, we had already started working on solutions to that problem. Most importantly, we wanted to give fraud ops the ability to create and modify the rules in our fraud detection logic and thus decrease the reaction time. We also wanted to give them more data to use as input. We produce lots of data in general. For example, we detect the document type, we have data on how confident we were in that detection, but this data wasn't always readily available for fraud detection purposes. And it also had the problem of discoverability. With the amount of data that we produce, finding the useful bits in there was kind of like trying to find a couple of needles in a hay bale. And we were also hoping that doing all that would unlock perhaps some unforeseen and useful use cases. So the first part was bundling the most important data for a given verification. We built a simple API service for that with Fast API that basically just gathered data from our various internal APIs, and it also did the curation of selecting only the most important and useful bits. We store that data as a flat dictionary with hierarchical human-readable keys. For example, document information like issuing country and type of the document are kept close to each other. And we also didn't want to create any central schemas and instead kept the format loose so that we could add more data and in general have an ability to iterate quickly. Once we had the data, we wanted to do something with it, and specifically we wanted to run queries against it. And we wanted those queries to be able to be written by the fraud operations specialists. So that meant that we wanted something quite simple and easy to use because we didn't want to require the fraud operations to have extensive technical knowledge. Because of that reason, we didn't go with something like SQL. Another reason for that is that we also wanted to keep it simple in terms of performance. We need to evaluate those rules in real time, and thus something like SQL, which gives you arbitrary complexity, could have really negative performance impact. And so we ended up with this pretty simple, pretty Pythonic language that had just some logical operators and comparison operators, exactly what we needed and not much more than that. Now, to use that query language, we needed to implement parsing that would take the human-written expression and transform it into machine-readable form, something like this. This is an abstract syntax tree that basically encodes all the important bits from the expression, like which data points we are referencing and what values we want to compare them with. And to do that sort of transformation to parse the original expression, we went with using PyParsing package, which is a special Python parsing module, as they say themselves. PyParsing had pretty steep learning curve, but I still think it's a lot better than writing your own parser from scratch because it handles lots of edge cases like quotation, escapes, and so on and so on. And to make this talk a bit more technical, here is also a short snippet of code of our parsing logic. As you can see, we start by defining some low-level blocks like what does a name look like or what is a value. Then we define some comparison operators, and finally we can use those as building blocks to build more and more complex parts of the expression. For example, here we have the comparison expression, which consists of name, then the comparison operator, and finally the value. And we can also control how the output looks like using the setParse action to make it what we want it to, and what you can see in this example again. Now, once we have this syntax tree, we want to take some data and evaluate that data against that expression and see if it matches. Again, the code for doing that is quite simple. We have some logical operators like AND here, which just uses recursion, and then some comparison operators. With the data and query language in place, we had just one piece still missing. We needed a tool where fraud operations can create and manage those rules, and we call that tool Sieve, as it helps us separate fraud from the good verifications. Sieve is both a service that evaluates the incoming verifications against the set of rules, as well as the user interface for managing that set of rules. And you can see an example screenshot here with a rule being added. In this case, it's meant to counter a case of farming fraud, which is when somebody tries to create accounts using other people's identities. And we can define the expression here, as well as say what should happen if it matches a verification. In this case, as we do usually, we send it to review to the verification specialists, but we can also decline the verifications immediately if this expression is really accurate at just finding the fraudulent cases. And with Sieve, we were able to create a rule that matched the fraudulent verifications from that Vietnamese group. We found one that looked for a combination of passport, something we saw on the image, and the result of some technical fraud checks. And they did try some new tricks to bypass our detection again, but we could now react much faster than before and make quick changes to rules ourselves and just stay on top of them every time. So let's do a brief recap. I have so far talked about how we gather data and how we take out the most useful bits. And I also showed how we created a query language that let us match the verifications against rules designed to catch fraudulent ones. But how do we create the Sieve rules? How do we know which data points to look for and what values to compare them with? And this is where analytics comes in. When we are defining the rules, we want to catch as much fraud as possible. We want to figure out the data points that find the fraudulent verifications and preferably find all of them. But at the same time, we also want to avoid flagging honest users as fraudulent. Otherwise, we could just mark everything as suspicious and we would find 100% of fraud cases, but we would also block all the honest users, and in the end, nobody would be happy. So, how do we help the fraud ops figure out which data points to use while also ensuring that the rules they create aren't overly broad? To achieve that, we needed the ability to do query verifications at scale over multiple weeks or even months. And we also wanted to use the same data and preferably the same query language. Now, theoretically, we could use our standard Postgres databases for that, because the data is there already. But we also needed the queries to be fast, to allow for iterations and our loose schema of the data didn't really play well with that, and using Postgres would just be too slow. So in the end, we built our own in-house tool called Verifications Explorer, which you can see here. It's a fairly simple tool for querying verifications using the same language. So you write an expression at the top part, and then you will see the matching verifications either as table or list view, or you can also see some exploratory analytics, like in this case, which countries are those verifications from. But to build this, we had some technical challenges. First, like I said, we wanted the queries to be really fast. We wanted responses within approximately 1 second. And those queries also needed to run against millions of verifications. And we had that loose schema data to deal with. And our first solution was a very simple in-memory database. We wanted to keep the data in memory to make the queries faster, and also to make it possible to do some additional processing on the results, like some statistical analysis. We decided to first keep all of that data as Python objects and Python dictionaries to keep it simple, and we indeed got that tool up and running really quickly. It was pretty straightforward. I can show here the expression evaluation code, which gives you the matching verifications. And as you can see, we just parse the expression that you give it, and then we just iterate over the list of verifications, which is our data set, and we just pick out the matching verifications. And you already saw the per item evaluation code before. Again, very simple, very straightforward. Unfortunately, that simplicity also came with some problems as we grew and as we wanted to keep around more data. First off, it was just slow because we were making lots and lots of Python function calls. We were looking at every verification separately, and that meant doing millions of function calls, which are pretty slow in Python at scale. And secondly, it was also memory hungry because we kept everything as separate Python object without any optimizations at all, which meant that even keeping a simple number in memory would use 28 bytes of storage, a lot more than it should. So in order to be able to grow, we decided to implement version 2 of this and go with Columnar InMemory Database. Now, what does Columnar Database mean? Usually we save data in row-oriented fashion, as we did before. So, for example, here you can see that we have a bunch of objects. Each object has country and confidence, and you have values for all of them. In column-oriented databases, all the values of one column are kept together, usually in a single contiguous list. And firstly, this matched our data access patterns a lot better because we only use a couple of columns per query, but then we look at all the values within that column. And secondly, having all the values of one column together meant that we can also use the fact that they have a single data type, and we can then use something like a NumPy array to store them and take advantage of the associated performance improvements. And that became the first bigger goal of our implementation, to store everything in compact arrays. We could have used NumPy or Pandas or some other options for that, but in the end we chose PyArrow because they have good built-in handling of nulls, and also their set of accelerated operations matched our needs. And then we just had to implement a bit of a layer of custom logic on top of PyArrow. But showing you some evaluation code again, here is very similar code to what you saw in the simple version. So the core logic did not really get much more complicated. we still first have some code for logical operators, just using recursion, and then the comparison operators. And the main thing that is different is that instead of looking at single values, we now operate on entire arrays. And we use the pi-arrow compute functions like the BC equal that you see in the bottom here, which instead of looking at a single value, take the entire array and evaluate that. But to get to this simplicity, we needed to do quite a lot of pre-processing. First off, we needed to detect the data type for each column. Although that also gave us ability to handle some more complex parts as pre-processing steps. So, for example, we could see that if we only have small integers in one column, then we could use something like column of or array of 8-bit integers to save that and save lots of memory as a result. And we also needed to do some pre-processing for the expressions themselves to make sure that the values that the user used are corresponding to the values of the columns, so that you couldn't compare a column full of numbers with a string, for example. So, despite some challenges, the results were pretty good. We set out to improve the query speed and the memory use, and the query speed got sped up by roughly 100 times. It depended on the exact query. Some of those were just sped up by around 20 times, others multiple hundreds of times, but 100x seems like a fairly medium value there. And we also managed to reduce memory usage by 7 times, or to put it another way, we could keep around 7 times as much data with the same amount of RAM. And another important part was that the results of our queries were now the same pi-arrow arrays, which also meant that the additional analytics, like calculating some statistics on the results, was also accelerated and much faster. Now, you might also be wondering why we didn't use any existing solutions, and there were 2 reasons for that. First, with a custom solution, we could tailor it exactly to our own use cases without having to compromise on anything. And secondly, we wanted to have some really quick solution at the time. And especially thanks to Python's ecosystem, we were able to get to working solutions quite quickly, and probably faster than it would have taken to set up some complex existing solution. That said, as Veriff keeps growing, we are looking at some external solutions these days to serve as the next generation of the same thing. And so, to kind of wrap this up, what this work enables us to do is, first off, the fast queries. We can search for verifications using arbitrary data points in seconds or even milliseconds. It also contains some analytical features. For example, we can find common data points, meaning we can ask which data points have similar values in all of the matching verifications. And this often serves as a starting point for fraud operations to create rules. For example, they might see that 85% of all the matching verifications in this dataset have a specific version of Android, and then that can become a basis for a new C rule. And in the end, all of that has led us to respond to new kinds of fraud much more rapidly, and has basically changed how we tackle complex fraud. And obviously a lot of that has been made possible by Python ecosystem and lots of existing packages that let us iterate quickly. I mentioned Fast API and PyParsing and pi-arrow in this talk, but really most of Veriff's automated verification logic runs on Python, including various machine learning packages, data science packages, and so on. And so in the end, thanks to our ability to analyze verifications at scale and quickly, we were able to find out some data points that let us catch those fraudulent verifications that I started with. One of those data points, interestingly, was a piece of furniture. Do you remember the C rule that I showed earlier? We run simple object detection as part of our verification logic, so we detect all the objects on the images we receive. And we noticed that this group was using a red pillow as a background for all the document photos. And this showed up as the cushion image label, and it became one of the data points that we used in the C rule to defeat that group. And in the end, after some back and forth, they gave up and went away. I said in the beginning of the talk that my team is all about finding patterns and then using them to stop fraud, and this is exactly what happened here, even if the pattern was a bit unusual. Let me finish by saying thanks to my own team as well as fraud operations. They are the ones doing all the hard work. And also thanks to the PyCon organizers, and most importantly, thank you for listening.
Very good talk. Thank you very much. We have some questions here, but is there anything that you'd like to
Thank
say
you.
now that you're actually here in person? Before we get to that.
Yeah, I just hope you enjoyed the talk. Let's do the QA, I guess, and then we have a little announcement regards the winners of the quiz that we had in the Veriff booth today.
All right, great. First question, quite a lot of votes, but I think you maybe went over the answer already. But for these expressions that you wrote, why the need for the parser? Why not instead have the operators write actual Python and then use some sort of Python interpreter that's safe, and then avoid the steep learning curve of developers having to learn how to make a whole parser and making the queries being more powerful as well? Why not this option?
So basically, why didn't we convert this simple query language into Python and then evaluate the Python?
Or more just have the people, I think, in this dashboard, have them actually write Python, like have them have access to this variables, and they can write whatever expression they want, rather than just
this. That would kind of go against the whole keep it simple approach, because we needed the evaluation to be quick performance-wise. We didn't want even the possibility of making anything too complex and slow there. And also, I would be very wary of giving people access to full programming language like Python there, because of, well, the same reasons pretty much.
Yeah, there are some libraries which think AST eval, which can be used to do some things, that is quite limited. But yeah, I believe you're even breaking down these expressions and getting statistics based on each expression for the thing, which would be completely impossible if you went down that route. So very good answer there. Bit of a snarky here. So you're preventing children from making purchases online, but this is more, or can you make any interesting stories regarding underage people trying to use the system?
Well, one thing we often see underage people do is trying to use their parents' driver's licenses. And yeah, we try to prevent them, perhaps not from making purchases online, but from getting their parents' car or the driver's license and then signing up and driving somewhere.
Other questions here, mostly doing with speed. And why did you choose Python for making this as opposed to some more performant language like C or C#?
Well, Python usually gives you packages that already have the heavy calculations optimized, like PyArrow in this case, or same with any other data science and machine learning library. And then Python just becomes this glue code, and it's a very efficient and easy to use glue code. So you can take the libraries that give you the performance and just combine them with the simplicity and ease of use that Python gives you. And I don't think that we would get the same results or the results as quickly with something like C++ or anything else, even if the pure performance might be very slightly better.
Yeah, it seems quite flexible because you were able to do this initial prototype and then build something more while still getting the advantage of C under the hood of this Pyro. And for the data structure you had, you decided to go with a flat JSON structure rather than a nested one, but you had this like nested notation in there. What was the reason for this?
We wanted to just avoid the complexity of nesting. I think also in the data that we store, but more importantly in this query language, and basically we wanted to hide the actual nesting from the user, if that makes any sense.
And are there actually any arrays inside of this structure, or is it just straight key value pair and the value is just always a native type?
We actually have lists as well, yes, as one of the potential data types, which created some complexities that I didn't go into during the talk. But if we had stuck with just numbers and strings, for example, then things would have been even easier.
And another question here about querying is that, did you try any existing query languages, search databases, like these GraphQL or OpenSearch?
Not really. We did think about SQL at first, but I'm not honestly even sure how GraphQL would be applicable in this situation. But yeah, not really.
Looking here, those are basically all the questions here. There's one asking about using Redshift or Snowflake for Power Analytics. Did you consider these, or what was the main selling point?
It might be something that we could look into in the future, but like I said, we needed some quick solutions at the time, and then integrating and building on a complex external solution, it didn't seem like the best idea. But yeah, as we grow, I fully expect that we outgrow any homegrown solution at some point, and then the question is indeed which external one to go with.
Yeah, makes total sense there. Thank you very much for the talk.